This is part 4 of circuit design. Now we're going to talk about a situation when the microcontroller does not have enough energy to drive the load. Uh, the microcontroller is a sensitive circuit, and in order for it to be programmed, it uses a lot of different components inside. It's an integrated circuit. It doesn't have a lot of power. So for small devices like LEDs and buzzers, the microcontroller is well suited to drive these loads directly. But if you want to use the microcontroller for operating high voltage and high current components, unfortunately it just does not have the energy itself because it's a very sensitive device. In order for us to drive high current devices, then we're going to need to include some type of driver circuit in between the microprocessor or microcontroller and the load. In this discussion, I'm going to explain to you the principle behind this idea. So hopefully you'll get a clear understanding of what's really happening electrically within the system. First, let's start off with a general concept that I've explained earlier. We know that you need an energy source in order to operate a system. You need a source of energy. So let's call that a power supply. Sometimes you might need more than one different power supply depending upon the energy needed by the system. But in this example, let's assume that this power supply was designed to operate at a fixed voltage of 5. And this power supply has the ability to provide about 1 amp of current. Well, that's more than enough current to operate many types of loads. For example, let's say I have a motor over here. I'll change the color to blue. Let's say I have a motor. And this motor requires about 200 milliamps of current to operate. Well, that's more than enough current. The power supply has more than enough current to operate this motor. As a matter of fact, this power supply can operate 5 of these motors, each motor using 200 milliamps. And we discussed before that you can connect through a switch to this motor. If this is a 5-volt motor, for instance, you can close the switch and current will flow through the motor and the motor will run as expected. So we can switch the motor on and off. However, we said this has a limit in terms of its operation. Therefore, we decided not to connect the power supply directly to the motor. We decided that we would use a microcontroller between, and we would use the microcontroller as a programmable power supply, meaning that we can write a program and it will decide when to turn the power on and off. And it operates at 5 volts. But we also learned that with normal or typical microcontrollers, you're only going to get about 20 milliamps of current coming out, and you can only receive about 25 milliamps of current going in. So either way, this microcontroller would not have a chance to operate this motor directly. In order to operate this motor, we can't go through the microcontroller. Somehow, we have to go around the microcontroller and get this 1 amp of current into the motor. Okay. One way to do that, one way to do that is to use something called a driver circuit. Now, a driver circuit may seem complicated idea, but actually a driver circuit is one of the easiest ideas to understand if you understand the principle of how a transistor operates. If you recall from your electronic devices class, you probably remember that a transistor has 3 regions of operation. You probably learned that the transistor has an active region, a saturation region, and a cutoff region. Now, in your electronics class, you probably focus a lot on the active region because you were focusing on using the transistor as an AC amplifier. And you didn't talk too much about the saturation and the cutoff region. But in digital circuits, the saturation and the cutoff region is the primary focus. You also learned about the transistor when you were beginning your studies that if you have a small amount of current into the base, it will control, if set up properly, a much, much larger amount of current in the collector. Now, there are many mechanical analogies where you can use a small force to move a much larger object. So this is not new. In this case, what we're going to do is we're going to use this transistor to transfer some of the energy from this power supply. So now what you have is you have a little bit of current going into the microcontroller, and you also have some extra current that I can use for another component. Now, when that current will be used will be determined by how I operate the base of the transistor. So if I use the microcontroller to control the base current, then I can use that microcontroller to control a collector current or a much larger current in the system. So where do I want that current to go? Well, I want the current to go into the motor. That's where I need it. So what will happen is the current will come into the collector junction, flow through whatever it's made of, come out of the emitter, and then finally it will make its way through the motor. And where do currents always flow end up after it has made its way through the component? Where does it always end up? It ends up back to the negative part, or we call this ground. Now let's look at this from a voltage standpoint. You can go to your data sheet and you will learn that when the transistor is in the saturation region, the voltage between the collector and the emitter is usually very small. Therefore, if I start off at 5 volts, I only lose a small amount of voltage between this point and this point, which means this point will probably be close to 5 volts. In this example, let's use 4.5 volts. 4.5 volts between here and the other side of the motor is more than enough voltage to operate this motor. It may not operate at the full 200 milliamp capacity, but it will certainly be very close. And the current that's needed to operate the base or to operate the transistor is probably only maybe 1 milliamp to perhaps at maximum 5 milliamps. So as you can see, now the microcontroller does not need to operate the motor at the 200 milliamp. It only needs to turn on the transistor. So now you have a two-step process. Step number 1, the microcontroller turns on the base. Step number 2, because the base is turned on, the collector is turned on. The collector passes current through the transistor to the emitter with very little voltage drop between the collector and the emitter, and now that current is allowed to flow at a much higher level through another component. Now if you think about this path, you can see that it doesn't matter whether I put the motor on the emitter side or whether I put the motor on the collector side, because once again it's just the same continuous path from 5 volts to ground, and you still have the same principle of a power supply driving a load. The only difference now is that you have an electrical switch. So let me make the analogy for you so you can understand clearly what's going on. What you have essentially is a power supply, a switch, your motor, and ground. But this switch is not a mechanical switch, it's an electrical switch. And as with all electrical devices, there will be some type of voltage drop across this electrical switch. But you can use your imagination as this just being a switch that you can open and close. When the transistor is in the saturation region, you can say the switch is closed. But when the transistor is in the cutoff region, then you can say the switch is open. And this switch will be controlled by your microcontroller. In part 5 of this problem, I will talk more and more about the driver circuit, but I wanted you to understand the principle and not to be confused anymore about how driver circuits work. Driver circuits do not provide energy, it only switches energy from the main power source. Finally, I want you to understand clearly that you know this principle before. You have dealt with this principle many times in your circuit analysis course. This is just basically the theory of parallel circuits, where you have one power supply providing current to multiple networks. In our example, the first network would be the microcontroller, and the second network would be the motor. And you can add other networks, perhaps a lamp. The only difference is that you are using the microcontroller to turn these other two networks on and off by using perhaps one output and maybe another output. But it's still the same principle that you learned in your DC circuits class, where you have one power supply and other components connected in parallel. I want you to feel very comfortable with this principle. Thank you.